Okay, now we look at solving crack problems in linear elasticity. What we mean by that is linear elasticity, and in fact, isotropic linear elasticity is valid everywhere in the domain that we are going to consider. So, this is what the problem looks like. This is a crack, and this is sitting. This is a single crack. This is a sharp crack. All of these words are important. This is a sharp crack because this face and this face are virtually touching each other. They're infinitesimally apart, so they are basically touching each other, so that this tip, the crack tip, is infinitely sharp. So the crack works as an infinitely sharp stress concentrator. It is an isolated crack because this crack tip lies in a, in a domain which is infinite in extent. So this crack tip does not see any of the boundaries, or are not affected by any of the boundaries or any other defects that are in the vicinity. So there is no interaction between this crack and the boundary of the body, nor is there any interaction between this crack and another crack. Usual rules of linear elasticity apply. So we have tractions applied on some parts of the boundary, which we denote by gamma t, and then we have displacements applied at some parts of the boundary that we denote by gamma u, and the total boundary is gamma, which is union of gamma u and gamma t, and then gamma u and gamma t don't have an intersection, which means that you cannot have a part of the boundary where both tractions as well as displacements are applied, but in all parts of the boundary either traction or displacement must be applied. So these are usual rules. N is the outward normal. So what I have written here is the Cauchy relation applied to tractions that are applied on the surface, outer surface of the body, which is at infinity. This stress sigma naught, the naught denotes that this is the remote stress, very far away, applied very far away from the crack tip. So we are interested in this problem to solve the equations of elasticity in this region that is very close to the crack tip. We want to figure out what is happening locally at the crack tip. The crack boundary, the upper boundary, we call it as C plus, and the lower boundary is called C minus. So these are the two crack boundaries, and then now the boundary of the body is the remote boundary very far away from the crack plus the crack boundary. This together forms the boundary of the body. For the time being, we assume that the crack boundaries are traction free, so no tractions are applied on the crack boundaries. All tractions that are applied are at the remote boundaries, that's shown here. Okay, so we can recall the governing equations. So the governing equations of equilibrium is this. We have learned this in elasticity. We are going to assume that things are slow. So the loading is slow. Things don't vary much with time, very fast with time, so that accelerations are small, and therefore this term is almost equal to zero, which gives us the static equilibrium condition that we have learned in elasticity, and we are going to use that for the time being. We will relax this condition later if time permits. Boundary condition, as I said, that displacements are specified on gamma u, tractions are specified on gamma t, and the tractions are related to the remote stress sigma ij0 by the Cauchy relation. So this relates the applied tractions to the applied stresses. And on the traction free crack surfaces, traction free is important, none of these tractions are on the crack surface. So on the traction free crack faces, C plus minus, which are located at theta equal to plus minus pi. So if you go back, and if I put the axis here, this is x1, this is x2, centered at the crack tip, and this is my r, and this is my theta. The first crack tip crack face is located, the upper crack face is located at pi, and the lower crack face is located at minus pi. So these two are also traction free surfaces on theta equal to plus minus pi. And now apply the Cauchy relation carefully. Let's go back and apply it. Let's erase this. So here are my axes, and this is r and this is theta. This is theta, and the crack is located at theta equal to pi. The normal to the crack is therefore 0, 1, 0. This is the normal to the upper crack surface, and this is 0, minus 1, 0. These are traction free surfaces. Apply Ti equal to sigma ji nj, and you will find that T1 is sigma 2, 2. No. You'll find T1 is sigma 1, 1 and 1 plus sigma 2, 1 and 2 plus sigma 2, 3, 1 and 3, out of which n1 and n3 are 0 on the upper surface, and this is 1. So T1 is equal to sigma 2, 1, T2 is equal to sigma 2, 2, and T3 is identically equal to 0. Okay. So there is, firstly, there is no out of plane traction. T3 is equal to 0, and T1 and T2 are sigma 2, 1 and sigma 2, 2, but T is 0 on the upper crack face, which implies that on theta equal to pi, sigma 2, 1 is equal to 0, sigma 2, 2 is equal to 0. Okay. Now, if I use the r theta coordinate system, I can easily see that on this face, on the upper crack face, sigma 2, 2 is equal to sigma theta theta. So sigma theta theta, remember, is this is sigma theta theta at the crack tip, and if you make theta equal to pi, then sigma theta theta and sigma 2, 2 coincide. Similarly, sigma 2, 1 is equal to sigma theta r, which is also equal to sigma r theta. So we can write at theta equal to plus minus pi, that is on the upper crack face and lower crack face, sigma theta theta, sigma r theta, both are equal to 0 for a traction free surface. We have proved that for the upper crack face. For the lower crack face, we can prove it in the same way. The normals are 0, minus 1, 0. We apply Ti equal to sigma ji nj, and in the same manner you will be able to show that sigma theta theta and sigma r theta are equal to 0. You have to keep these, you have to use the Cauchy relation very competently in this course. So if you are confused by these reasonings, please go back and learn your Cauchy relation properly. So this is the traction boundary condition that I'm going to apply on the crack faces. This is the traction boundary condition of the remote edges, gamma t, and these are the displacement boundary conditions applied on the remote boundaries, gamma u. So this is my problem definition, and then I am going to use isotropic elasticity, which means my stress strain relation is given by this. This is isotropic elasticity, and these two are the Lami's constants. So these are Lami's constants, which are again related to the elastic constants E and mu in the usual manner. Again, you should go back and look at the tables of the relations between the elastic constants for the isotropic solid to figure out how these are related to Young's modulus and Poisson's ratio. The strain displacement relations for small strains, we are again going to use small strains here. uh, this are the strain displacement relation, which we also write as epsilon ij equal to half u I comma j plus u j comma I. So uh, this is an alternate form of writing this. As I said, we are going to assume quasi-static loading. We are going to assume quasi-static loading. The accelerations are going to be zero. And later, if we have time to do dynamic fracture problems, we'll relax this and see how it affects the solution. For right now, the equilibrium equation will be handled without the right-hand side term. So we are going to do quasi-static. We are going to assume that the crack grows not very fast, and the loadings and displacements applied also don't vary much with time. So with that, let us put the axis at the tip of the crack. R theta are as defined here, and we can find now, we are now interested in finding the state of stress here. This state of stress we can find in r theta coordinates, in which case we will take a small box of this shape. We can also find it in the xy coordinate system at the same point, and in that case we'll take a small box which is of this shape with edges aligned with the x1 and x2 axis. Now at the same point we can use either of the two coordinate systems. First we will use the r theta, and this is the xy coordinate system. In the xy coordinate system, these would be my stress components. Sigma 22 is what is known as my opening stress. Sigma 22 is what is known as an opening stress. Sigma 11 is a stress along the crack line. So remember one thing carefully, that the x1, x2 axis that I have taken is aligned with the crack. X1 is along the crack line, X2 is perpendicular to the crack line. So the orientation of the X1, X2 axis is determined by the orientation of the crack. So X1 axis will always be along the crack line. So sigma 11 is the stress along the crack line, sigma 22 is the stress perpendicular to the crack line, and the stress perpendicular to the crack line is called the opening stress. Again, sigma 12 is this should be sigma 13. This sigma 12 and sigma 13 has got interchanged, so this is sigma 12, this is sigma 13. So sigma 12 is like this. This is your sigma 12. Sigma 13 is out of the plane. Sigma 13 is out of the plane. We will deal with sigma 13 later, but this is known as the shearing stress. So this is the stress that is trying to shear an element in the plane of the crack. Shear an element in the plane of the crack. We will stick to plane stress or plane strain. Mostly to plane strain, which means that this yellow body is infinite in the x3 direction. Plane stress would mean that the yellow body is very thin in the x3 direction, and the crack runs all through the body. It's a through crack. Okay. For the time being, we want to reduce this to a two-dimensional problem, so we consider a through crack which runs along the x3 direction, whose front runs along the x3 direction. By the way, I'll call these as the crack faces, this as the tip. So these are the faces, these two are the faces, these are the tips, and if I look from the top, this would be the view of the crack, and this is the crack edge. So this is your x3 direction, and this is your x1 direction. So get the geometry correct, and the crack runs all through the body. So the body is this thick, this is the thickness of the body, and if this is infinite, it's a plane strain problem. If it's very small, it's a plane stress problem. So we will generally be dealing with plane strain, but as you know, plane strain solutions can easily be converted into plane stress solutions. Okay, uh, this is one way of looking at it. The other way is, at the same point, I use the cylindrical polar coordinate system, in which case this is how my stresses would look like. Now, uh, I take an element like this. So this would be my sigma RR. This is my sigma theta theta. And this would be R theta. Right? And the out of plane stresses are sigma zz. Out of plane stresses are the same as in the Cartesian system, but this is what we will turn to first. By a stress transformation, the stresses that I get for this infinitesimal element can be transferred into stresses that I get here at the same point. So we can easily do that. We'll solve the problem in this coordinate system, and later we will show the results in this coordinate system as well. Now we are interested in stress states very close to the crack tip in this region, very close to the crack tip, far away from the boundaries. So that's why we call this an isolated crack. And this solution was given in 1957 by Williams and is called the Williams solution. Okay, so now this solution has, before we go into the solution, we have to we have to make sure that we understand a few concepts. First is we assume that this crack tip never leaves the plane. It moves in a path along the plane if it moves at all. If it moves in a path along the plane. And this is at the moment a stationary crack. It's not going anywhere. It's just on the plane. All the loading is on the plane. And then I can divide the loading into two parts. Okay, and the two parts are a symmetric part and an anti-symmetric part. Symmetric part means symmetry about this axis, symmetry about the crack axis. And symmetry specifically means that if I take a point here, and if I take a point which is a mirror image of it about the symmetry axis, which is the crack line, then the stress state here is a mirror image of the stress state here. So that means sigma 11 and sigma 11 has to be the same. Sigma 22 and sigma 22 here has to be the same as well. Sigma 12 will change directions. That is easy to see. If this is the mirror, then this stress reflects as this stress reflects as this stress reflects as this, and this stress reflects as this. So sigma 1 1 and sigma 2 2, the normal stresses, do not change sign and are identical. The shear stress is identical in magnitude but is in the reverse sense. That is what symmetry means. And the symmetric state can be realized if we apply only a sigma 2 2 in the remote at the remote locations, remote boundaries far away from the crack tip, or we only apply a displacement in the two direction at the remote boundaries. If we do either of this, either we apply sigma 220 or u20 at the remote boundaries, this crack will only open, and this the top face will open as much as the bottom face because these two are equal. You are pulling the crack in this manner, and therefore we can expect a perfectly symmetric situation for the stresses, where the stresses at the top and at an mirror plane below a mirror plane on the bottom, and its reflection on the bottom has the same normal stresses but shear stresses reversed in sign. Okay, so this is known as the opening mode or mode 1. Mode 1 is also called an opening mode. So if we only apply a opening mode, where we are only trying to open the crack, then we have to apply U20 or sigma 220, and that is what is known as an opening mode. Okay, the other possibility could be that we apply remote stresses that are in the 1 2 direction, so we apply either remotely sigma 120 or u10. So what we are trying to do is we are trying to move the upper crack face to the right, and the lower crack face we are trying to move it to the left. So the crack is known as to be in its shearing mode. In the shearing mode, you have perfect anti-symmetry. Perfect anti-symmetry means that if we consider this to be the symmetry plane, the normal stresses change sign at a mirror point, but the shear is in the same direction. The shear is in the same direction, but the normal stresses change sign. That is the perfect antisymmetric mode, and that can be obtained by applying only sigma 120 or only u10 to the right on the top and to the left on the bottom, or vice versa. You can reverse it, in which case it still remains an antisymmetric mode. So this antisymmetric mode or shearing mode is known as mode 2. So opening mode is also a symmetric mode, and mode 2 is a shearing mode or an antisymmetric mode. So if you apply your remote stresses in the plane, so you are looking at the 1 2 plane, so the remote stresses that you can apply are sigma 1 1, sigma 2 2, sigma 1 2 0. So you can apply sigma 1 1 0, in which case nothing will happen to the crack because sigma 1 1 0 is along the crack line. If you apply sigma 2 2 0 only, you are in the opening mode. If you apply sigma 1 2 0 only, then you are in the antisymmetric shearing mode. If you apply u20 only, you are in the opening mode. If you apply u10 only, you are in the antisymmetric mode. But any combination of this, any combination can be applied, in which case your solution would be a combination of mode 1 and mode 2. This is all that you can do by applying stresses in the plane. Okay, you have only three stresses in the plane. So if you sigma 110 does nothing, sigma 220 and sigma 120 are all that you can apply. So mode 1 and mode 2 are all that you can apply. Now you can have another mode which we are going to study, um, which is mode 3, where you apply this. So you apply sigma 230, sigma 230 uh, on the top and the bottom in opposite direction. So this means that sigma 230 is going into the plane. Sigma 230 is not a stress component in the plane. It is going into the plane, and here sigma 230 is coming out of the plane. Either you can do this, or you can apply U30 going into the plane below and U30 coming out of the plane above, which means that you will actually be in mode 3, or a tearing mode. So this part of the body, this part of the body above the crack is trying to come out towards you, whereas this part of the body below the crack, this part of the body below the crack is trying to go away from you. So you are trying to move this crack in this direction by pulling the upper part and pushing the lower part. You could do the reverse. You can do the reverse also, and still you would be in mode 3. So mode 3 is an anti-plane mode. Mode 3 is an anti-plane mode because the stresses or displacements that you give at remote boundaries are not in the plane. So this is mode 3, or the anti-plane mode. Okay, so these are the three modes that are possible uh, for crack. Nothing more is possible, and any loading of the crack will be a combination of mode 1, mode 2 and mode 3. Okay, so the modes you have to understand very carefully, because we will use them all the time. So once you understand the modes, let us solve for the in-plane modes first, and we will solve for the anti-plane mode separately. So let us solve the problem for mode 1 and mode 2, in which case the problem is strictly two-dimensional, because all the stresses that you have applied lie on the plane. The body has a plane strain, body has plane strain conditions applied to it, so it's a problem that can be solved in a two-dimensional setting. So let us handle that problem first. While handling it, you have to remember that the opening mode is a symmetric mode, where the stresses, normal stresses, are do not change sign and are equal in magnitude above and below the symmetry line, whereas the shear stresses change sign, right? And uh, mode 2 is the shearing mode, where it is completely antisymmetric, which means that the normal stresses are going to change sign, whereas the shear stress remains, the sign of the shear stress remains unchanged for mirror points across the symmetry line. Okay, we will handle mode 3 separately. We are just handling mode 1 and mode 2 now. So uh, okay, um, so this Williams solution starts from the biharmonic equation. This you know. We are trying to guess a Airy stress function for this problem. So we are going to solve this in cylindrical polar coordinates. So you must also be aware that in cylindrical polar coordinates, the stresses are given in terms of the Airy stress functions, Airy stress function, by these expressions. These have been taught to you in elasticity, and that in polar coordinates, the harmonic operator is given by this. This is the harmonic operator in the polar coordinate system, and the biharmonic operator is the harmonic operator applied twice on phi. Okay, so with these, just recall, after recalling these, let's go on to try and guess what kind of phi we should take. Now, if you go back to this problem, if you go back to this problem, you'll see that uh, this is a problem where there are no length scales. What do I mean by that is, uh, in this problem, the crack extends infinitely to from 0 to minus infinity, and the body is infinitely large. Okay. When this is the situation, there are no length scales in the problem. So there is nothing that is a characteristic length scale special to this problem. Everything is far away at infinity. Now, in such situations, uh, the airy stress function that I'm going to choose has to be such that the units of r, or units of x1 and x2, length units, do not matter. So if I took a photograph of this and enlarged it, I would see a bigger crack, but the bigger crack will look locally exactly the same as a crack looked at in, say, the micrometer scale. So whatever scale you use for the length, you are going to see the same picture uh, every time, and you won't be, if I give you the two pictures, you will not be able to tell whether this is taken at a micrometer scale or at a millimeter scale or at a meter scale. Okay, so in such cases, uh, we expect that since the form of phi has to remain the same no matter what the length scale is, we expect that uh, the expansion would be of the form of this, which separates the r and the theta functions. So it's first of all, this phi should be separable in r and theta, and the variation in r should be of the type r to the power alpha. So this is because if, say, I measure r in meters, then r is some meters to the power alpha. If I measure it in millimeters, it is say 1000 r. So whatever is in meters becomes 1000 times of that, and then but still the form of the equation remains the same. This function is not affected by the change in length units that I may use. So whatever length units I change to, uh, the form of phi will remain always the same, and that is expected because this is a scale free problem. There are no length scales hidden in this. If there was a length scale hidden, and I you can think about this, if this was not separable, say this was also a function of r and theta, then I cannot guarantee that if I change the length scale, the form of the function will remain the same, right? uh, so that is the reason why we are going to choose a separable solution in r and theta, and we are going to choose the function of r as a power function, and this is what we are going to take. So we are going to take phi as a function of r to the power lambda plus 1 times f of theta. Okay, and if you do this, then uh, del square phi, so del square we have already specified for cylindrical polar is this, and del square phi you can show it easily. Del square phi can be written in this form, and del 4 phi, which is del square of del square phi, del square operator already becomes this, so you apply this twice. So the del square phi is this, which is now fourth order ordinary differential equation in f theta. It's not a function of r. The function of r we have already assumed to be of the type r to the power lambda plus 1. So we have nothing to find there except for this lambda, what this lambda is going to be. That's what we are going to do in this course, in this class. And this is what del 4 phi, the biharmonic equation, looks like. And for this to be true, either the del theta square of lambda minus 1 whole square of f theta has to be equal to 0. So either this has to be satisfied. This is a second order differential equation, and the solution of this you already know is this, with lambda minus 1 being the stiffness here. This is lambda minus 1. This is of the form del x square plus k x equal to 0, where k x is f theta and k is lambda minus 1. So this is the solution of f theta if this is true, and this is the solution of f theta if this is true. If since this is a fourth order differential equation, then you have four constants here. Now the total solution of the fourth order differential equation can be a combination of these two. So the most general solution would be of this form, which is a combination of the lambda minus 1 and lambda plus 1 terms, right? uh, just for the sake of because we are going to need them to calculate the stresses here. We need derivatives of phi, and for derivatives of phi we need the derivatives of f theta. We keep the f theta derivatives calculated. And these are these complicated looking expressions. With the derivatives, first and second derivatives of f theta and f theta defined, remember there are four constants to determine still. We have not determined them, but to derive the stresses in terms of these constants is easy, and we just put them in the stress equations, and these are the stresses that we derive for this problem. Okay. So these stresses, the what we don't know is what is lambda, and what we don't know is what are the forms of these f theta function. What is the form of this f theta function? Okay. Now let us imagine that my crack is, let us first imagine that my crack is a wedge. So wedge is something like this. It's not sharp as a crack. So the two faces of the wedge are not infinitesimally close to each other. So this is still x1, x2. This is still r and theta. But this angle is alpha and this angle is also alpha. So it's a wedge for which theta equal to plus alpha and theta equal to minus alpha. At theta equal to plus alpha and theta equal to minus alpha, again here sigma theta theta and sigma r theta will be 0. Here again sigma theta theta and sigma r theta will be equal to 0. So these are the traction free edges of the wedge, and we apply the boundary conditions at theta equal to plus minus phi. These two things are 0. So sigma theta theta is here, sigma r theta is here. If I put so I replace the expressions for f theta and f prime theta that I have developed here. So f theta is this, f prime theta is this. I replace theta by plus minus alpha everywhere, and then what I get is sigma theta theta at theta equal to alpha is equal to 0, and sigma r theta at theta equal to alpha is equal to 0, which establishes that this phase is traction free. I do the same for this phase also. I get two more equations. I put theta equal to minus alpha, and I get these two equations. Sigma theta theta and sigma r theta are equal to 0 on the lower phase. So these quantities are 0 on the lower phase as well. I have four constants to determine. I have four equations, 2 from theta equal to alpha and 2 from theta equal to minus alpha. I can solve them in theory and determine C1, C2, C3, C4. But before doing that, what I'm going to do is I am going to try and split this into a symmetric and an anti-symmetric problem. So obviously these parts cannot be 0. These parts cannot be 0 because then lambda will be a trivial trivial quantity. This part cannot be 0, and this part cannot be 0, this part cannot be 0, the rest of it can be 0. So I rearrange the equations, subtract them and add them from each other to derive four different equations, slightly different equations. You can easily do this. Uh, and these two, I do this because now I can solve them in groups of two. Okay, so this equation and this equation, which are obtained by adding and subtracting these four equations that you have, these two equations have C1 and C3 in them, whereas these two equations have C2 and C4 in them. Okay, so that is the advantage. Now instead of solving a 4 cross 4 simultaneous equation, I'm going to solve two cross 2 simultaneous equations, which is just more tractable. This is also a homogeneous simultaneous equation because the right hand side is 0. So for C1 and C3 to have non-trivial solutions, that means for C1 and C3 both to be not equal to 0, what I need is the determinant of this, determinant of C1 and C3 to be equal to 0. Similarly, for C2 and C4 to be not equal to 0, both not equal to 0, I need the determinant of these two equations to be equal to 0. So first let's look at C1 and C3. So I need that non-trivial solutions exist for C1 and C3, and then the determinant, this determinant is equal to 0, which if I multiply, if I carry out this determinant, leads to this equation. You should try this out. You should try out the steps. So this leads to this equation if you carry out this determinant. On the other hand, take the last two equations here, C2 and C4. We don't want them to be both 0. If they are not, then this determinant has to be equal to 0, and this determinant leads to this equation. Both equations look the same except for the signs, and now you can add them together, then this cancels out, then you will come to the conclusion that sine 2 lambda alpha is equal to 0 if you add them. If you subtract them, these cancels out, and you will come to the conclusion that lambda sine 2 alpha is equal to 0. Remember, these are for the wedge. These two equations have to be satisfied for valid values of lambda. So lambda can take only the values that satisfy these two equations. That is our condition. And now let us move to a crack. To move to a crack, what we have to do is we just have to put lambda equal to pi, then we will transform this problem, wedge problem, to that of a crack problem. So we are going to do that. If you do that, you will see that this is sine 2 pi, which means this equation is trivially satisfied, and for alpha equal to pi, this is the only equation that we will have to satisfy. So sine 2 pi, 2 lambda pi has to be equal to 0. That will only dictate my value of pi, my value of lambda. Okay, so that's what we do. We only have to satisfy sine 2 lambda pi equal to 0, and sine 2 lambda pi is equal to 0 when lambda equal to n by 2, with n equal to 0, plus minus 1, plus minus 2, etc. Okay, so this is my solution. My solution for lambda is that lambda is of the form, there are infinite numbers of lambda. There are infinite numbers of lambda, but lambda is always of the form of an integer divided by 2. The integer can be 0, plus minus 1, plus minus 2, and so on. And we are going to see which of these integers are physically accepted. Okay, now there's one important thing that we need to know. The important thing is firstly this: if my phi is of this form, then stresses are second derivatives, contain second derivatives of phi. So stresses contain second derivatives of phi. So this will contain lambda r to the power lambda minus 1. So if you look at your stresses, which we have somewhere, they contain r to the power lambda minus 1. So strains will also contain r to the power lambda minus 1. Okay, and the displacements are integrals of the stress. So displacements will contain r to the power lambda. So this is stress, this is strain, and this is the scaling of displacement. So the displacements will scale as r to the power lambda. Okay. Now if you come very close to the crack tip, r tends to if you come very close to the crack tip, r will tend to 0, r will tend to 0, and therefore all the terms where r of the form r to the power lambda, so remember your displacement scale as r to the power lambda, if you come very close to the crack tip, r tends to 0. So in the limit r tends to 0, if lambda is less than 0, the displacements will tend to infinity. If lambda is negative, then displacements will tend to infinity, which means that at this point you will have infinite displacements, which is just not possible. You cannot have infinite displacements. You can have infinite stresses in elasticity. You cannot have infinite displacements because that would violate the small displacement assumption. Okay, so we come to the conclusion that in this, among these possible values of among these possible values of lambda, uh, the ones with negative n are not possible because they would lead to infinite displacements. The one with 0 is also not possible. One with 0 is also not possible because that would lead to a displacement that is independent of r. R to the power lambda 0 would mean that the displacements are independent of r, but that is also unphysical because at the crack tip you have very high stresses. Therefore, you should have high displacements, and you have uh, stresses very high at the crack tip, and since the crack tip is a infinitely strong stress concentrator, the stresses should be high close to the crack tip but die down as you go away from the crack tip. So displacement should also follow something of that, some kind of a variation with the stresses, and therefore we cannot accept that displacements would be constant throughout for this problem. So lambda equal to 0 is also ruled out. So we are only left with the positive, non-zero positive values of n, which means now physically lambda can be half, 1, 3 by 2, and so on. These are the allowed values of lambda, physically allowed values of lambda. Now, for each of these, we have uh, one solution. So this we call as lambda 1, this we call as lambda 2, this we call as lambda 3, and so on. And for each of these, we will have one solution. So one set of C1 to C4. So we again rewrite these equations. So these four equations, simultaneous equations that we have, now that we have some idea of what lambda is, we know that lambda is n by 2 where n is positive, alpha is equal to pi. So with that, we rewrite these four equations, and these are those four equations. And now we put C1n here because C1, C2, C3, C4 are potentially different for each value of n. So for n equal to 1, it is something. For n equal to 2, it might be something else because this quantity will change as you change it. So for every set, you will have a different set of constants. For every n, you will have a different set of constants. That's what we envisage. Okay. Now, for n equal to 1, 3, 5 and odd numbers, when n is odd, this equation is identically satisfied. This equation is identically satisfied when n equal to odd, then cos of this will be 0, cos of this will be 0. This equation is also identically satisfied because this will be 0 and this will be 0. So for n equal to odd, you have only these two equations, and from these equations, given the fact that n is odd, this will be 1, this will be 1 as well, and you can find a relationship between c1n and c3n for n equal to odd. N equal to odd will give you c3n and c1n related in this manner. You should try this out again, and from this equation for n equal to odd, you will get, again, this is 1, this becomes 1, this becomes 1, and this becomes 1. For n equal to odd, you will get c2n is equal to minus c4n. So these are the relations that you will get between the constants. So for n equal to odd, only two constants are independent, the other two are dependent. Similarly, for 2, 4, 6, so for even values of n, uh, this will be identically equal to 0. So this will be 0, this will be 0, this will be 0, and this will be 0 as well. So these two equations will be identically equal to 0. So you will get a relation between c1n and c3n from here, because this will be 1 and this will be 1. So you will get a relationship between c1n and c3n, and between c2n and c4n you would get a relationship from here. This would be 1 and this would be 1. And for even values of n, this will be the connection between the four constants. Only again two of them are independent, the others are expressed in terms of this 2. So we have two constants for these values of lambda that we have chosen, and with these information we can write down the expression for the stresses completely, and the expression for the stresses would be written separately for n equal to odd and n equal to even. So uh, so these are the expressions for the stresses. The stresses are now sum totals of all of these possible values. So you have a sum over the odd ends and a sum over the even ends, and these terms are what we have derived so far. Uh, Remember, lambda is n by 2, so we have replaced lambda by n by 2, and r to the power lambda minus 1 appears here, so n by 2 minus 1 appears in all of these terms. So these are for the odd, and this is the series for the even, and n does not take 0 or negative values, it takes positive integer values only. Okay, so and we have used only one constant, two constants, c1n and c2n in this equation. c3n and c4n, we have eliminated them in favor of this equation for odd and in favor of this equation for the even terms. So this is the expression for sigma theta theta, which is derived from this expression, for sigma theta theta. Similarly, we will derive an expression for sigma r theta. We will also derive an expression for sigma rr. So that is easily done. It's just tedious. You have to collect the terms carefully. Sigma r theta again has a summation over the odd terms, again has a summation over the even terms, and then we have expressed everything in terms of c1n and c2n, in this case, and we have eliminated c3n and 4n. Okay, and sigma rr has only one expression, because sigma rr contains you can derive sigma rr and see why it has only one expression. So we can put it in, we don't have to split it into odd and even terms. We can derive it. Sigma rr is a less important stress, because it's component of stress, because it's in the direction of the crack. Sigma rr is in the direction of the crack. So these are the three stresses in terms of this infinite series. Now in all stress components, if you look at all stress components, you have the term r n by 2 minus 1. So n is 1, 2, 3, and so on, right? It cannot have negative or zero values. So the first term when n is equal to 1 is r to the power minus half. The second term, n equal to 2, is 0. The third term is r to the power 3 by 2 minus 1, that's plus half, and so on. So what you see here, as r tends to 0, that means as we move, so this is the crack tip, this is, sorry, your Cartesian axis, this is r, this is theta. As r tends to 0, that means as you move close to the crack tip, then these terms, this term is constant, these terms all go to 0, except for this term which has a negative power in it. In the stresses, this term has a negative power, so this is the term that's going to go to infinity. All other terms are going to go to 0. So in this series, as in the limit r tends to 0, this is going to be the most dominant term among the series. So if we are interested in uh, only the stress fields and strain fields and displacement fields very close to the crack tip, then this is the most dominant term that we should consider. All other terms will go to 0. Okay, so we can therefore um, we can go back to say the equation for sigma theta theta. We can take the term for n equal to 1 and drop all other terms, odd or even, because they are going to go to 0 as r tends to 0. So in the limit r tends to 0, all other even and odd terms except n equal to 1 can be dropped from this. Every stress component contains n by 2 minus 1. So this logic applies to every stress component uh, in the plane problem. Okay, so if I do that, then this is how I can write it. I retain only n equal to 1, so now I have replaced it with C11, C21, and these are the three stresses that I can write. And again, r to the power n minus 1 is r to the power minus half, so I have this 1 by root r singularity for the stresses. So this singularity for the stresses exists for the dominant term, and uh, we have used to eliminate the constants. We have used these expressions which are valid for n equal to 1. Remember, we have two independent constants and the other two constants are related to them. We have to use the relation for odd terms because n equal to 1 is odd. So these are the relations that we use. Using that, for the first term, these are the stresses, in plane stresses that we get. Okay. Uh, I hope it is clear why we chose to retain only the first term and eliminate the rest. Obviously, obviously, at some point of time, some distance away from the crack tip, these terms will start competing with this term. So as r increases, this term will start competing with this term, and there this approximation that we have done, that the first term n equal to 1 term is the most dominant one, will obviously fail. But beyond that limit, closer to that limit, r to the power minus half or 1 by square root r is the most dominant term, and that is what we will deal with at the moment. We will look at the effects of the next term at least in a few classes from now. So uh, so these are the stresses at the crack tip. So I will stop here for the moment, and um, we will sort of rearrange these equations a little bit and try to show how mode 1 and mode 2 are both hidden here uh, in the next class.